We're going to talk a little bit about the XX communication, which is the privacy layer of the XX network. So XX networks were first introduced by David Chaum in 1979, and then a more formal technical paper in 1981. And mixed networks to this day remain probably the most secure mechanism for building an anonymous communication protocol. And the way they work is essentially you just forward a batch of messages from server to server. And as you can see in the bottom diagram, each one reorders them. And as you can't see is that they're re-encrypted or decrypted so that you can't correlate numerically input to output. And then once they get to the end, they are kind of fully decrypted and the information necessary to deliver them is made available and they're delivered. The fundamental problem in this approach is that all of these encryption operations are blocking relative to each other. You have to mix and decrypt the entire batch of messages before you pass it on to the next node. And the same thing and the same thing. So what ends up occurring is that these time-consuming public operations end up taking a very long time, and the latency of passing data through a mixed network of sufficient size to really be valuable. So, this example has 3 that wouldn't give you much anonymity protection. Sufficient size is hundreds of thousands to millions. And once you get to that size, the speed of these networks is too slow to be functional, or historically they have been. So as a result, the world has come up with other alternatives that don't have as good security properties, things like onion routing and other structures. So in 2016, David Chaum came back and published his paper on cMix. And cMix is unique because it takes this mixing structure and it enables it to run at reasonable speeds by taking those complex computations and figuring out a mechanism to execute them before the messages are received. And as a result, while the network still has to do the computation, the users of the network don't experience the latency resulting from it. Now, Elixxir has been working to implement its variant of cMix, which integrates full end-to-end encryption and is able to defeat not just the basic idea of mixing, but also further mechanisms of metadata analysis. So one of the other things that can occur is that if you don't have ununiform packet sizes can be used to figure out what's going on. So if you see a packet of exactly 93,124 bits going on one side, and then somewhere else you see a packet of the other size come out, there's no other packet of that size, well, you're likely to be able to figure out the 2 are the same. So cMix breaks up packets into uniform packet sizes so that such attacks can occur. The other problem is packet timing, which is that if packets come in at a certain time and then leave at a certain time, even if they're kind of jumbled with other ones, you can kind of figure out which one is which. So cMix uses this batching process whereby messages are processed as a large group, which eliminates timing issues. So by combining all these things, combining pre-computation, we've delivered a network which actually you can use right now with the XX Messenger in its alpha state, which is able to anonymize messages with relatively low latency costs. The network as it stands, I think, has 6 seconds latency, although the current structure doesn't take full advantage of pre-computation, and we expect it to get down to possibly 1 second by the time of BetaNet. I want to go back because we have a question here about the database gets compromised, and this really answers the question, which is that every single node would have to reveal how they mixed messages and how they encrypted them in order to de-anonymize messages. And that's fundamentally how we answer this question, which is that there isn't a singular database. There's not one place which would have to be compromised. So we have here a kind of example of a mixing network and how the anonymity works. So as you can see, you have in this a 3-node setup, and 2 users are passing money into the network to be exchanged. And the coins passed in are mixed together, and the BP cannot tell which coin is which, where they came from, or even how they correlate. So the blue individual in this case sent 6, but the BP can't tell, and also can't tell where it came from. And also we can't either because we can only see the central node. In fact, if we can only see one node, we still wouldn't be able to see where money went or where it came from. So it's a fairly powerful technique which is able to scale to thousands and thousands of transactions simultaneously at relatively low cost.